Hi, I'm Craig Lawton, Principal IoT and Cloud Architect based in Melbourne, Australia. I've worked with governments and universities the last 5 years, helping them with projects around cloud, automation, IoT, and yes, smart cities. I'm going to show you today how to build a cost-effective, scalable and secure smart city backbone using native AWS services. It's a fun way to learn about IoT and data analytics, which have become increasingly important to cities this year, who have required up-to-date situational awareness and heightened responsiveness. We'll look at architectural patterns for IoT, connectivity and data analytics, including a deep dive on LoRaWAN, a popular networking technology. And we're going to show you all this through a demonstration. Smart cities are resilient cities. They can respond to changes or new citizen requirements really quickly. Native AWS services allow you to respond quickly in a secure, cost-effective way, as we take care of the undifferentiated heavy lifting and all the services pay as you go, allowing you to scale as required. So what are smart cities? There are many definitions out there for a smart city. To me, a smart city brings together IoT sensor technology, connectivity, and analytics to provide new services and insights. And it's all about improving the quality of citizens' lives. A city needs strong foundations, however, and AWS regions with their multi-availability zone infrastructure provide the reliability and capacity needed. Cities are very complex too, and you often need to collaborate with third parties. And the AWS marketplace is a great place to find these partners to collaborate with. And lastly, cities come in all sizes, so it's important that you can scale up and down to your city's needs. And when thinking about an architecture for a city, it's important to have a solid architectural backbone. And if you get these components standardized and considered up front, it really helps you later on. Decouple the ingestion, which includes your IoT and integration and third-party sources, from your data lake. And then also decouple your data lake from the data consumers, whether that's AI, ML workloads, analytics, visualizations, etc. And you shall have a future-proof data foundation where you can control and manage access to your data. By following this approach, you can extend more easily. Perhaps you want to add a contact center that accesses the data lake with Amazon Connect, or add an Alexa skill, or even build a digital twin. Today I'll show you how to build this architecture using our native services. All of these services have pay-as-you-go models, so it means it's scalable, cost-effective, and responsive. For ingesting data, we're going to look at AWS IoT Core and also time series databases with IoT Analytics and Amazon Timestream. For our data lake, we're going to use AWS Lake Formation, which simplifies data lake setup and manages a lot of the underlying services. And then finally, we're going to look at using Amazon QuickSight so that we can create great visualizations and dashboards for our data. I'm going to give you a quick overview of our demo now so you know what's in store. We're going to use the IoT device simulator from our IoT solutions page to generate traffic. It's going to generate parking, bin and air quality data and send it to our core service. And you can see the data coming through. We're going to use the IoT rules engine to route that to Timestream database and also through IoT analytics and add in the latitude and longitude data through a Lambda function at the pipeline stage. And that's going to allow us to create these geospatial visualizations for our 3 different demo data types of parking, bins, and air quality sensors. In a smart city, you often have many sensors for things like bins, parking, and air quality monitors. And the Internet of Things, or IoT, has led to a proliferation of low-cost devices to perform these many functions. When it comes to smart cities, it's known or comes under the category of massive IoT. The viability of IoT use cases rests on the cost of devices, but also the cost of managing, and that includes connectivity. And we find with things that many of them have constraints around energy, network, or price, and that's led to an emergence of new networking technology known as low-power wide area networks. We're all familiar with local area networks. They have great data throughput, good range, but usually just typically within building. Power is not a major concern, but these can be quite expensive to set up with the structured cabling and switching costs. Perhaps you might think mobile or cell networks are great for IoT. And it's true, you get great data rates and great range within a city, but your battery life can be pretty poor, as we know from our smartphones, and it's not that cheap either to use these. So this is where narrowband and low power wide area networks hit the sweet spot. They have great range. They can communicate from devices to gateways over tens of kilometres. The battery life is great. These devices can be out in the field for 5 to 10 years before the batteries need replacing, and they're quite cheap. The trade-off, and we're familiar with trade-offs in architecture, is that you don't have great throughput. But for many smart city use cases, you don't need to know whether your smart bin is full every minute of the day. You maybe only need to know every 15 minutes or every hour. And some of the most popular narrowband and low power wide area network technologies are Sigfox, LoRaWAN, and NB-IoT. But I'm going to focus on LoRaWAN today because it's proved incredibly popular with the smart cities customers I speak to. It uses unlicensed spectrum in the sub-gigahertz range, so that contributes to its cost effectiveness. You have to be mindful that in different geographical regions there are different spectrums to be used. As you can see, the range is up to 20 kilometres, which is really awesome in a country like Australia where I live, where you have really spread out geographical areas. And it's managed under the LoRa Alliance, and Amazon is a sponsor of the LoRa Alliance. And if we look at a LoRa and LoRaWAN architecture, we can see devices can connect to multiple gateways, one or more, and then those gateways connect up to a network server, and then the network server manages the device registry, the data and control planes, and can forward that information onto an application which you can think of as a destination. At a physical and link layer, it's communicating using LoRa from the devices to the gateways. And then from the gateways to the network server, it's communicating with more traditional network technologies that you may be familiar with, like TCP and UDP. And then from the network server to your applications, it's along the lines of what we're used to with cloud computing. If we look at the payload, from the devices to the gateways and the gateways to the network server, you're actually only transmitting bytes. So you'll just see a hex string coming through. And that contributes to the real cost effectiveness and low power nature of these networks. At the network server, typically there's a payload conversion which converts bytes to JSON. Devices come typically with the scripts and the functions to do this conversion for you. So how does LoRaWAN integrate with AWS IoT? So there are many popular LoRaWAN vendors, and you can find them in the AWS marketplace. For example, Actility and the Things Industries. And you can deploy those solutions into AWS, and you can deploy them in a highly reliable way with multiple network servers spread out over different availability zones. We've worked very closely with these partners to collaborate on a CloudFormation template to integrate with AWS IoT. And these CloudFormation templates are supported by the vendors. If we look at these integrations, you deploy them as a CloudFormation stack, and then it'll take care of integrating with AWS IoT. It'll synchronize the device attributes, including the registry information and attributes about your devices between their network server and AWS IoT's device management registry. It'll forward on the messages so that they come through, which is great. It'll manage the shadow states, and you could also do payload conversion if needed. And once you're in the IoT core service, that allows you then to very quickly, using our rules engine, route the data to other services like S3, Dynamo, and Lambda. So LoRaWAN is a very popular technology for cities, and it's easy to integrate with AWS IoT now. As I said, the data comes in MQTT protocol, and it comes in JSON format. And for today's demo, I'll be using our IoT device simulator to generate those JSON payloads for simulated devices, which are known as widgets within this simulator console. This solution is available to all customers on our solutions page, and you can deploy that in your account. The solution creates a web application, and you can see the screenshot there called Sim Console, and you can see that you can use this console to generate the traffic to our IoT core service to simulate our IoT network and devices. Now, city data often has a geospatial aspect. We've got these devices, but we need to know where they are so we can place them on a map. So for our fictional bins, parking and air quality sensors, I've placed them on a map of Las Vegas. It's not real Las Vegas data, but if you wanted to build this demo and use real data, it's important to know that most cities have open data portals these days, and you can find out where these assets are by going to those open data portals. The First thing that we did in the simulator was create 3 device types. And these 3 device types we created using point and click and the sim console. And they were for the bins, air quality monitoring, and parking. We then loaded Las Vegas data from a CSV file we'd created. We put it in an S3 bucket, and that triggered a Lambda function to load the actual instances of our devices, our simulated devices, into the simulator. They're called widgets, so we'll use that term from now on. But we could have created these widgets through the IoT console, but then you would have had a random widget ID, and we needed to have a predetermined widget ID so that we could use it to look up lat and longitude later. And finally, that Lambda function also created a new DynamoDB table and loaded our latitude and longitude into that table so we could look it up later and place our devices on a map. Now the simulator is running and it's pumping the widget data through, and it pumps it to IoT Core using MQTT, and they're posted on a known topic, and you can see the 3 topics there for smart air quality, smart bins, and smart parking. IoT Core has this great feature called the rules engine. It allows you to select using SQL-like statements some or all of the messages and even some or all of the attributes, and enrich the data even as well. And then you can take 1 or more actions on it. So for our data from our 3 devices, we've got 2 rules for each device. 1 to send it to an action that will send it to IoT Analytics, and 1 to send it to an action which will send it to Timestream, and we'll show that soon. Other common patterns we see customers use, they sometimes have an action to send it to Kinesis, which can act as a buffer to decouple the ingestion from upstream systems that may be down, and also to batch data up to make a more cost-effective architecture. And also we see customers use Lambda functions and actions. So you could have an action, for example, that looks to see if a bin is greater than 80% full, and a Lambda function could integrate with a city work order system to send somebody out to empty that bin. So IoT Analytics, just looking at that workflow, it validates the data is within specific parameters, and then it pumps that through a channel into a pipeline and then ultimately onto a data store. We've set this up for each of our 3 device types. At the pipeline stage, there's the opportunity to transform or enrich data. We're using a Lambda function now to add back in the latitude and longitude of our assets. The data store is an IoT time series optimized data store, and we've chosen for our demo to use a customer managed S3 bucket to make it easy to integrate with our data lake. IoT Analytics also allows you to create SQL-based queries and create data sets, and you may want to do that to optimize your environment. Looking at the Lambda function, which does the latitude and longitude lookup, the way it works is the pipeline can send a batch of messages at a time to the Lambda function. That batch is a list of events, and if you can see the for loop there, it's iterating through these events. Each event is a dictionary type, and you can see that we've done a DynamoDB lookup on the IoT sim location lookup table, and we've added in the latitude and longitude table. A very simple piece of code. The other route, or the other destination for our IoT data, is Timestream. It's a very quick way to set up a managed time series database. You can configure the retention for the in-memory components and also the magnetic components. There's 2 concepts you really need to understand with Timestream, and that is dimensions and measures. A dimension is an attribute that describes the metadata of a time series, and in IoT that's often an attribute about the device, something like the widget ID or the device ID. And measures, and that's the actual value being measured. So it might be something like temperature, for example, or in our example, the bin level. So let's have a look at our demo at how this works for our ingestion. So I've used the IoT solutions to create our device simulator. We've deployed that as a CloudFormation template, and we can see the stack deployed here. When the stack has been successfully deployed, there is an output created which points to the web console for the sim console. And we can see that there, we can click on that. And this is what the device simulator looks like. You can see we've got 51 widgets generating data to our AWS IoT service. If we click on device types, we can see how we've created a smart bin, a smart parking, and a smart air quality device type. And if we look into the smart bins, we can see the type of attributes. And we can see that it's posting device messages on smart bin. It's sending a message every 60,000 milliseconds, and we can see that it's sending the fill level, last collection date, and also the device ID through in the payload. If we go back, we can see that the widgets are generating data. We can see from our console here in the simulator that it's actually generating data, and the widgets that we created in this console were created from this Lambda function, which imported the CSV information into these tables. That first table is the widgets table. That's part of the simulator CloudFormation stack. And you can see the second column here is the widget ID. This is from our CSV file. And that's one that we predetermined so we could look up the geospatial information later. That Lambda function I briefly showed also imported from the CSV file the latitude and longitude and put that into a new DynamoDB table we've created for our environment called the location lookup table here. And if you have a look at that, you can see the device ID is the primary key, and that matches to the device ID in the widget table and the latitude and longitude. So it's pumping that information through, and we can go to the IoT core service now and use the test client. We can subscribe to a wildcard topic. Hash will show you all the messages coming into IoT core, and we can see here in the console the messages coming through, in this example for smart air quality. So we know that data is coming from the simulator, and now we can take action on it and send it to Timestream and IoT analytics. Now, before we could set up Timestream, we need to go in here and set up a database for smart cities, and then we set up 3 tables. It's easy to set up a table, and this is the screen you see. We've set it up for a table for bins, air quality and parking. If we go back to the IoT service, we can create a rule. We've created 6 rules here, 3 for Timestream and 3 for IoT analytics. The Timestream rule for smart bins selects those measures, fill level and last collection date from our topic for smart bin, and it has one action to send to a Timestream table. You can see it's sending it to the smart city and the smart bin table, and you can see the dimension is the device ID. So we've set up the rule, set up the plumbing now for that data to come through to Timestream. If we jump into Timestream and have a look at the smart bin table, we can see our time series database by clicking preview data and run, and then having a look at that particular table, and we can see how the data is structured and the way it comes through. For IoT analytics, we first of all set up a channel, if you remember in our flow, and then on the other side we set up a data store for our data to land in. Our data store, and we'll show it here for Smart Bin, is a customer managed S3 bucket with that name there that you can see on screen. And to have the data come through, we had the pipeline in the middle connect the channel and the store. You can see at our pipeline stage we're executing a Lambda function, and this does the latitude and longitude lookup. When you use the console to set up a pipeline, it shows you the data that's coming through. You can see the activity we have is the Lambda function. You can see the Lambda function there listed, and we're doing it with a batch of 1, so we're doing 1 message at a time. And then you can click Update Preview, and you can see what this Lambda function is doing. It's adding in those lat and long fields, which are provided there in green. So we can see that the data is coming through our both IoT rules now to IoT Analytics and Timestream. In our IoT Analytics data store, which is Customer Managed S3, we can see how our data is organized here. We can see that ultimately they're landing as gzipped JSON files. So one of the best ways, if not the best way, to organize your city's data is in a data lake. And this is great because you can store all types of data, whether it's IoT, video, call transcripts, anything at all. And we find cities have these very common challenges around different silos of data and providing a consistent and automated approach to security governance and being able to scale to their needs. And AWS Lake Formation really simplifies the setup of data lakes. It helps coordinate and configure Glue and Athena. Glue helps you crawl through these data at rest in your S3 bucket and catalog them. Athena allows you to do queries, SQL queries on that data at rest. You can put in IoT data into your data lake because you put any kinds of data. I have a customer who brought in occupancy data from IoT sensors, and they also built in building management systems and also utilities data using traditional integration methods. And they use that data to understand how to optimize their energy costs and have saved hundreds of thousands of dollars this year. Lake Formation also gives you granular table level controls to all your data, similar to a traditional RDBMS. And with Athena, you can save your queries. So if you want to optimize and do queries and use them again later, you can use that. Your data lands in an S3 bucket, but we also see customers have staged S3 buckets where they move the data through several buckets and they apply some structure or processing along the way. And you might want to do that if you want to modify your data to be a smart city standard like Firewire or OASC. So let's have a look at Lake Formation security and how it's set up with the Glue crawler jobs to discover the schema and catalog the data so that we can run queries on it using Athena. So if you recall, we landed our data in our customer managed S3 bucket in our data store. We can see here how the data is organized. It's one S3 bucket for all our types, and you can see how it's put them into separate folders and organized and partitioned them by time. You can see that the files are created as JSON gzip files. If we go into lake formation, some of the things we've set up, we've disabled IAM access control, so we're using lake formation permissions. And also we've gone in and created these special permissions for different roles. And the important one I wanted to point out was the lake formation workflow role, which is used by Glue to manage lake formation permissions. This is all covered in the Getting Started guide for lake formation. So this is pretty much copying that verbatim. And you can see the lake formation workflow role here, which is used by Glue. If we jump into Glue now, we can see that I've set up 3 crawlers to crawl our data. They're running every hour, and so that keeps our catalog and data up to date. If we jump into Smart Bins again, we can see that it's using that particular lake formation workflow role, and you can see it's scanning the Smart Bin folder of our data store. The first time the crawler runs, it creates a table, and that table has been stored in our Smart City database we created in Glue. If we click on that table for Smart Bins, we can see that it's discovered the schema for our data, and the lat and long have added back in. And we'll briefly have a look at air quality and also the parking data. And you can see at the top some table parameters like the record count and object count, and you can see that the information is being kept up to date in our lake formation data lake. Now we can run some queries on that data at rest, all without having to set up a database at all. This is Athena. We can select our Smart City database, and then we can preview the data from these tables. And we can see the kinds of data that's coming through. If it's air quality like this, you can see the battery life, device ID, lat and long, etc. If you look at Smart Bins, you can see that the fields for Smart Bins. And the great thing about Athena is these queries can be used by anything with a JDBC or ODBC connection capability. So you can use your preferred analytics tools to access this data. So now that you've built a strong foundation for your city using our regions and availability zones, AWS IoT and a data lake, you want to make use of that data and generate visual insights. And customers love Amazon QuickSight because you don't need the guys in the white lab coats to actually build visualizations, and it has very simple per user, per month costs. And this is really important for cities looking to uplift their data capabilities within budget constraints. Customers also find solutions to help them with this space in our AWS Marketplace, solutions like Domo and Open Datasoft, for example. But QuickSight is dead simple to connect to a cloud-based data source. And in our example, we're going to connect to our Timestream tables to generate charts, and we're also going to connect to Athena to look at our data lake-based data, and that includes the geospatial field, so we can put that on a map. So let's see how this is set up in QuickSight, so QuickSight can access your underlying data sources, and how we can create a quick dashboard, and then we'll show you some dashboards we set up to illustrate the art of the possible in this space. So firstly, with QuickSight itself needs to be able to access the underlying AWS services. And you go to Manage QuickSight, and then on the left there, Security and Permissions. And here you can select which services you access and also which S3 buckets you need access to. So in the QuickSight Security and Permissions, you'll see that we've clicked Access to Athena there, and you can see S3, and you can actually select the buckets that it has access to, and you can see that we've clicked Access to our analytics data store. And you can also see that we've checked Timestream. So QuickSight can access the underlying services. The other thing is, if you're in a region that has granular permissions for QuickSight to lake formation, you also need to go in and look at what is known as the IAM allowed principle and make sure that that has access to select the lake formation tables. And then your QuickSight is set up, and you should be able to access both your Athena and Timestream data sources. You can see the data sets here that I've set up previously. The orange ones are Athena, and the grey ones are the Timestream data sources that I'd set up previously. We'll go through setting one up from scratch so you can see how to do this yourself. So when you click New Data Set, you can choose Timestream. We'll call this one Test, and you can create that data source. That'll then list all the Timestream tables that are available in your account. And we can click on Smart Bin just to be consistent. You have the choice then to import that to Spice, which optimizes and uses a lot of in-memory optimization for your queries, so they go blindingly fast. And then you have you go to the visualization screen. We're going to choose a line chart, we're going to put our time on our x-axis. We're going to put the measure from our Timestream database into the value. And then we're going to use device ID to color map these. And then you can see the visualization very quickly gets created for our time series data. But we've created these other ones from scratch. So this is for parking data. You can see we've created on a map of Las Vegas the current status of all our parking spots. On the left, we've got the amount of time it's been unoccupied in the last 30 minutes. And we've also got some charts there we're generated from our parking Timestream tables as well. If we have a look at air quality, we've done some geospatial visualizations as well. This shows where the air quality sensors are, and the size of the circle indicates the size of the measurement for parts per million and carbon monoxide. We're using a heat map on the left there to show how these measurements are changing over time. And also, as you can see, air quality data is great to put on charts as well, so you can see trends. And then finally, we've looked at our smart bins. If you have a look at our smart bins, you can see we've created a visualization which shows in color whether a bin is over 80% full, and that could allow operations to go quickly. We've also used ML Insights, which is part of QuickSight, to see which bins are filling up the quickest. So you can do a lot of interesting visualizations very quickly with these native AWS services. So to recap, we set up an IoT device simulator, we created 3 device types, and then we imported widgets from a CSV file so that we could look them up later and understand where they could be placed on a map using geospatial information. The messages from our different device types came through, and we took action on them using the IoT rules engine. We sent the messages to Timestream tables and also to IoT analytics channels. In IoT analytics, at the pipeline stage, we executed a Lambda function to look up the latitude and longitude of our devices so we could place them on a map. And then we stored the data in a time series optimized IoT analytics data store that was a customer managed S3 bucket. And that customer managed S3 bucket formed part of our lake formation setup, which allowed us then to use Glue to catalog and crawl that data, Athena to make those queries available. And then we use QuickSight to generate charts and visualizations that could be used by city planners. So it's no matter what stage your customer is in, we have mechanisms to support them. If you've got opportunities in this space, you could reach out to a specialist solution architect like myself. We have a prototyping lab that can help you build prototypes with 2 to 3 week sprints. And also we have professional services that can come in for longer paid engagements to help you get started. If you'd like to have a go at building this yourself, there's a great YouTube video which can get started very quickly with AWS IoT and Amazon Timestream. And I've also got some links here for the different getting started guides for the documentation that we used to build this demonstration, so you can experiment with these different services yourself. And if you'd like to learn more around what cities are doing with AWS and some of the solutions they're building for citizens, we have an ebook that was recently released, and there's also, I'm pleased to say, an Australian and New Zealand version that you can download here. And if you work with cities or for a city and you've done some great digital transformation work in the last year, we have our annual City on a Cloud competition, and entries close December 15. So if you have a chance, please jump in and submit your submission. And lastly, we have a wide range of architectural resources to help you with best practices, whether it's the well-architected framework and the labs that go with it. We also have a bunch of architectural resources you can use to get guidance on how to build things. And we have a solutions library where there's a lot of solutions that you can build, you can take and tailor as well, like the IoT device simulator we've used for our demonstration today. And if you'd like to learn more about smart cities in your regions, we have smart cities leads in regions around the world. Feel free to reach out to them directly, and we would love to hear about how we can help you further. So thanks for listening today. I trust you've learned something new about IoT and analytics and how you can build cost-effective, scalable and secure smart city solutions and backbone using native AWS services. Thank you very much.